everyone to AstroAI launch seminar. And today we are very happy to have two speakers who will talk about different aspects of AI and machine learning. So first, Festa Bucinca will tell us about physical models, how to extract physics from models, in particular in the case of galaxy titles, and she will tell us a little bit about symbolic regressions, other interesting topics. And then Belén, you, the second speaker, will tell us about improving rates of detections of asteroids with CTF data using machine learning. So again, this is supposed to be a very active conversation. So if you guys have questions during the talk, you're welcome to ask. And then after, we'll go outside and continue the discussion out there. There should be some food out there. All right. Take it on, Festa. Thanks.
Perfect. Hello, everyone. My name is Festa Bucinca. I'm a candidate at the University of New York. I'm working with Viviana Corviva. Similar to the spirit of this center, Viviana is astrophysicist with expertise in machine learning. Maybe you've seen her book come up this summer, Machine Learning for Physics and Astronomy. And my other advisor is Ari Mahler, who is an astrophysicist with expertise in galaxy formation. So our project that we've been recently thinking about is whether we can use machine learning tools to extract physical models in the galaxy formation scheme. Specifically, we've been focusing on the problem of galaxy sizes. Now, galaxy formation is hard. We all know that. It's really hard. And even if we know in a simulation the physics that goes in at the beginning of the universe, it's not that we really understand necessarily what's going on and how we're getting the properties we get at the very end at redshift 0. So what we're trying to do is not easy. We're trying to model, in a way, all this complex physics plus the evolution with data with properties at redshift 0 only. Now, in this video, you can see a formation of this galaxy. This is from TNG collaboration. And here you can see the formation of this galaxy, the gas component, and here in the instead, which is not really visible, is just the stellar component of it. So this is just one of the many examples. Now, among all these very complicated problems, we've chosen to focus on galaxy sizes. Most galaxies have a component that is disky, and then another component that is the bulge part. So most galaxy sizes are disky plus bulge. Disk galaxies have a different mechanism. They are rotationally supported, while bulge galaxies, spheroids, ellipticals, are all pressure dominated. And then there's this third group, which is even more complex, a mixture of the two, and we really don't know anything more about that. So for rotationally supported galaxies, a natural instinct, which also comes from early theory in the field, is that maybe angular momentum is conserved. So this is what early theory in galaxy formation tells us. Galaxies form as gas collapses in the dark matter wells of the halos, and then because of this, it's gas and also dark matter halos. Dark matter particles have the same tidal torque. They experience the same tidal torques, and so angular momentum conservation leads to a simple picture of galaxy sizes, which was proposed by Mao and White in 1998, where the size of a disk galaxy is proportional to the spin and the size of the halo. Unfortunately, we don't have a simple model like this for bulges. So, is that really the case? Most of the recent literature in hydrodynamical simulations does not find a correlation between galaxy sizes and galaxy and halo spin. So we don't really know if this beautiful, simple theoretical model holds. And in this work, we propose a pipeline, a workflow where we can use machine learning to basically track any galaxy property that we are interested in, see if the information in the data set provided is there regarding that galaxy property that we want to know, and then if at the end we can come up with a physical model. Now, for galaxy sizes specifically, The workflow in our case is we use as tools machine learning to first ask if the information is there about galaxy sizes, and if yes, if there's a small number of features among all those available that actually drive prediction, and if so, then we use symbolic regression to extract what we call a physical model. So we, at the very end, come up with an equation, which we call the physical model. Now, a great setup to apply this kind of workflow are the semi-analytical models, simply because in semi-analytical models, we know the ground truth. So what we use in this work is semi-analytical models, the Santa Cruz SAM, which is run on merger trees extracted from PNG hydrodynamical simulations. So for those that do not know semi-analytical models, you take the dark matter merger trees, and then you basically write clear recipes into how each property of the galaxy is formed. So this is how they work. To make everything more realistic in this work, we use a half mass radius instead of just our disk. So we basically measure the size of a galaxy, because this is what is usually measured in observations as well. Okay, so machine learning we use in order to learn if the information is there. The features that we employ are a set of 31 features at redshift 0. And here you can see some of those features. We feed these features into 2 machine learning models to learn whether the benchmark of information is there or not, and we predict the half mass radius. Now, when we look at the results of these 2 models, we are encouraged because we think that the information is there. Now, in the left panel, we can see the predictions from a random forest model with those 31 features. And we measure the performance of these models using the R-square metric. Simply, the R-square metric is a correlation between prediction and truth value. So in the case of random forest model, we get an R-square score of 0.92, which is promising. And then we use the support vector regressor as a more sophisticated machine learning model. And we see that it performs slightly better. The test score goes up to 0.94. So yes, we're encouraged that there is information that machine learning models can really predict galaxy sizes given these 31 properties. And so now we ask, is there a minimum number of features, like a basis set of features, a core set of features that drives prediction rather than all this large amount of features that we have available at hand? And in order to learn this, we carry on add feature ranking analysis, where we start by using, in the first row here, 31 models. So we take one feature at a time, and we run a complete model using just one feature. And then we record the score of that feature, the performance of that feature. And then we choose a feature that has the highest performing score. And next, we fix the first feature, and we run the number of pairs of features that are left, and we choose the pair with the first one fixed that performs best. And we carry on like this until we either run out of features or we reach a performance plateau in the R-square score. So basically, we choose one feature and we add one feature at a time until we run out of features or we reach the maximum. And with this process, what we learn is that there is really this basis set of features that contributes to the prediction of galaxy sizes in our data set. And it's only the first 6 features. So when you look at the plot here, the R-square score increases as you add each of the first 6 features and then saturate. So the features that actually contribute to the prediction are halo spin, stellar mass entering via mergers, stellar mass, rotation velocity of the disk, bulge mass, and velocity dispersion of the bulge. And so now we're encouraged to use this core set of features, this basis set, to search for a physical model. So what we do next is we take these 6 important features and we run symbolic regression to find an equation that relates input and output using a mathematical analytical formula. So the equation that symbolic regression comes up with is the one you can see here, where size is proportional to spin times star payload, which I encourage you to recall from the first slide in theory, where we expect that a galaxy sizes are actually proportional to spin times the size of a halo. And then some other terms, which also kind of make sense physically, because we have an m ball times star term, and then we have this 1 over v, this v term, so velocity with this, velocity with the halo. We look at the performance of this model, of this equation, and we see that it's not great, but it's encouraging. We have an R-squared score of 0.80, so there is room for improvement, especially when you look at the schedule around here. We next wonder, what if morphology is at play? Because we know that the sizes is.
Yeah, sorry, do you mind if I interrupt? So if I'm following this correctly, so what you've done is you've created a semi-analytical modeling that you have the simulation running at certain points, and then based on the state of the simulation, you apply some physical laws to derive some of the properties of the galaxy.
Yes, so the part where you run some semi-analytical models to come up with properties of galaxies at the very end is like a project of its own. So what we actually did was just take that data as a data set and then apply machine learning.
And then you take some physical properties like star formation rates and mass of the bulge, etc., and you try to predict the size.
Yes.
Why did you guys choose to do that rather than the opposite process of taking something that you can measure from data and then predict some of the physical quantities like the star formation rates and other things?
Something we can take from the data, meaning.
Well, in the sense that you can measure the size of a galaxy, right? And then you can take observables like mass of the galaxy and then try to recover things that you cannot directly observe, like say the star formation rate or something.
So we were inspired by two reasons. One is this theoretical model by Moe and White, which says that galaxies are proportional to the halo spin times the size of halo. And this has been the theory for a very long time, but we don't really know if that holds. Like, even if we can measure in observations, in theory, how that really happens, like how the story goes, we don't really know. And this project specifically was interesting because in this case, we kind of tested the machine learning workflow, whether it can come up with a result that we already know exists. And if so, then we can apply the same workflow, which is what we're doing now, in the simulations where we don't know what goes into setting galaxy sizes. We have sizes, but we don't know the physics behind it. And so we want to know if like machine learning can help us extract some information about this puzzle that's been going on for quite some years now.
Okay, thanks.
Yeah, so as the next step, we used morphology because we expect like the sizes of disks and spheroids to be different. And so we color code by morphology, and here you can see the red and yellowish dots belonging to disk-like galaxies, and then purple and blue elliptical galaxies. And we see that the equation that we get from symbolic regression seems to behave well for the disk-like galaxies, and then it kind of fails for the elliptical galaxies. And so with this, we're encouraged to now search for an equation by morphology, where we kind of use now only a subset of perfectly disk galaxies. So we choose just perfectly disk galaxies. We feed those into the symbolic regression tool, and then we come up with another equation, which is size is proportional, again, to spin times our halo, which is promising because we expect that to be the case, divided by v bare squared. So we see here that there's no m bulge m star term, which again makes sense in the case of perfectly disk galaxies, we do not have a bulge. However, we see that with this equation, there's like the small size galaxies which have a constant size, but the equation predicts them to be smaller than they are. And so to fix that, we suggest that there's a minimum spin effective term that actually plays a role. So we redefine spin by using the spin effective term. And then with this spin effective term, the equation becomes more predictive. The R-squared score now goes from 0.92 over there to 0.96 here, and we don't have the problem of small galaxies anymore. So we have a functional form for perfectly disk galaxies. So now the next question is, how well does this apply to other groups of galaxies? So we divide our data set into 6 different groups, where group 1 is the perfectly disk galaxies, and then each of the groups we see an increasing portion of bulge up until the last 2 groups, where the last 2 groups are what we think ellipticals. And so this functional form that we came up using symbolic regression seems to work well for the first 4 groups, so disk-like galaxies, but it fails in the last 2 groups. We see that there's this term, the constant C, which changes from group 1 to point to group 4. It goes from around 1-ish to around 0.7, and now we come in with human knowledge, with like physics inside, and we say, what if this is just a linear term that depends on the amount of bulge that is available to the galaxy? And so we add this linear term, and we come up with a final equation where size is equal to 1.14, and disk m star times spin effective v disk v square square and r halo. Now with this physical model, it seems like we can predict galaxies pretty well. We have an R square of 2096, and all disk-like galaxies seem to follow the trend. You can see that there are no red dots in this plot, no ellipticals, so no bottle for that. This is very promising. Is that all data-driven? Not necessarily. We have some human input, some physics inside into that equation. And so as next step, we want to compare our data-driven equation with the real equation from the semi-analytical models. So up here you can see the equation that sets galaxy sizes in SAMs. It's a long equation, and I wrote out of it so you can know how complicated it is. The spin times R halo term are common with the spin times R halo term that we found using the machine learning workflow. And we want to compare this function here for the SAMs with the function that we're getting, which is much simpler, from the data-driven derived equation. So to do that, we plot the function in front of spin R halo as a function of concentration. And the red line here is that long function from SAMs in front of spin and R halo, while the green dots are the from our function, from our factor 1.14 v var over v disk squared. And it seems like we did get the right answer. So it seems like this factor that we found using machine learning actually captures all that long function in the SAMs. And finally, ellipticals, what do we do with them? So the first question that we ask about them is, do we have the information for ellipticals? So do we have enough information in our data set to predict ellipticals? So we look at the learning curves for ellipticals only, and we see that with the random forest model, the green slope here, and the test set, so it's increasing, which means that we don't have enough elliptical galaxies. So we need more galaxies in order to come to a conclusion whether we can predict elliptical galaxies with our features or not. And in order to solve this problem, we have 2 ways. So one is to use a larger box. The PNG 300 box has more galaxies, or we should use like some augmentation technique so that we have an equal distribution of both disks and ellipticals. What we're doing right now is we're running the same workflow for the TNG 300 box, where we have more galaxies, both disks and ellipticals. And with that, I come to the end of the talk. So in summary, can we discover a physical model for galaxy sizes using machine learning? Our answer is somewhat. Yes, we can use machine learning to learn if the information is there, and we can use machine learning to extract the minimum number of features that actually drive prediction. And we can use symbolic regression to guide us in the equation search, but we need some human insights and some physical knowledge in order to really come up with a final model. Yes, and our model is shown here, so now I can take questions.
Questions for Festa?
We have one online.
Okay, go ahead.
Yes, hi. This is very interesting, and it's a proof of concept. So this is great. So I'm just wondering, if you looked into actually real data at all to see how they behave, right?
Real data, you mean from hydro simulations or observations?
No, I mean observations. That's what I call real data, because these are TNGs, so you know the answer, and it's good to do this sort of thing. I'm just wondering how real data would behave. Have you worked on that?
I haven't worked on observations at all, but what I'm working on now is the TNG simulations, not the SAMs, which is in a way similar to real data because we don't have a recipe that really sets any galaxy property. So we don't know what goes on in the simulation to get the final property. So what I'm working on is a simulation, but not observations.
Thank you. Anyone? I don't know much about symbolic regression. I wonder if you could give us a brief
Yes.
summary of how exactly it works in terms of what is the input,
Yeah.
right? So it's, how does it actually work, the prediction of the equation, and whether, because you say you need some human inputs to actually integrate, whether you could input that insight previously as some sort of prior information to that process, or how does this work?
So as a prior information, I'm not sure. The symbolic regression is a package that Miles is constantly like updating and adding new features to it. But so the version that I have used so far, you need raw data, like the data in the data set that you use for your machine learning model. It requires a maximum of about 10,000 instances so that it can run. I mean, if you give more, it will take much longer. And then you have the ability to constrain the operators that you want to use. So that's why I think you need to have a physics insight when you really run it. Because if like you should constrain, let's say, how long the denominator in an equation should be. You should constrain how long or how complex a numerator should be. And then if you know the physics of the problem, you can constrain the power. Do you want it to be an integral? Do you want it to be this or that? You can constrain the operators that you want to use. If you're not expecting an exponential, then no need for that. Drop that out. Like just knowing your problem will be really helpful for the symbolic regression to come up with a good equation. And then symbolic regression has this trade-off, so it can come up with very complex expressions that don't really make sense. And it has this trade-off between accuracy and simplicity. So at the very end, when you run it, it will come up with the best equation, but you have in the files a list of equations, and then you can look at the other equations, and maybe you like a little more complex equation, but that makes more sense physically because you're the one to decide. Like you don't allow the machine to do all the work for you. So that's I think important when you use symbolic regression. And something else important. Okay, yeah.
So it's basically searching over a space of possible relations between these features, and that space is basically operations between them.
That's what I was going to comment. So you can't feed all the features that you have for symbolic regression, but it will carry out an internal feature ranking using random forest, just so that it chooses some important variables because it can not produce an equation with all possible variables. It will be too complex and it will fail by default. So it will do an internal feature ranking on its own. So it's better if you do that feature ranking and you just feed what you really think is important for the symbolic regression. Yeah.
Yeah, well, that's particularly go back to the slide where you shown the brain error that Can you just comment on the discrepancy between those? Because I mean, if I just look at this, I would get it isn't model.
Overfitting?
Yeah, so like your training error is much higher than your
that's R squared. That's an R squared score.
Yeah, but
so you think that it's overfitting with all the information, the train set?
If you just look at this would be my first guess. Because actually to me, like whether adding more data actually really helps.
I mean, yeah, so with this data set, we're unsure how much more data we'll have because ellipticals are complex by default. And so it's really a question whether even more data will help. But with this one, so far, it seems like it needs a little more data, and then we can come to a conclusion whether it can, like galaxy sizes and ellipticals can really be predicted with the amount of features that we have, which again makes sense physically because we have features at redshift 0 and elliptical sizes are set by also like the history, how mergers happen. So maybe we don't have enough information in the features for these galaxies. So maybe we need more features, or maybe we need a time series in order to predict galaxy sizes and ellipticals.
Yes, there's one more question. Did you want to follow up? Sorry. Did you want to follow up or? Oh, okay. Sorry.
Very interesting thought. I have actually following up question. Did you try maybe to make the hyperparameters? I don't have one quite system very sensitive. You tried.
Yes. Yes. I mean, I've used like hyperparameter tuning in all the steps, including those steps where I run one model features for every feature. Like I do have a parameter tuning even there so that I kind of get the most robust that I can get possible. So yeah. But maybe I can also check like how much better, if any, symbolic sport vector regressor can predict only ellipticals, and that will be another benchmark to know. Yeah, that's something I can do.
Thank you. I mean, I have some more questions, but I'll wait until we're eating outside to ask them, and people are welcome to continue the discussion afterwards.
Okay.
I think we're ready. Thank you so much.
Thank you.
Gonna switch gears now. We have second speaker, Belén. She's doing a PhD in Switzerland at EPFL. She's currently visiting Caltech, and she's been working with the CTF folks on the problem of asteroid detection using machine learning. So we're gonna switch to that. You are ready? Almost.
Yes, you want these to be here.
Yes.
Yeah.
Yeah, that is.
Well, hello everyone, and thank you very much for being here. I'm Belén, and I'm a grad student at EPFL in Switzerland. I'll be graduating at the end of 2025 and looking for postdoc positions, so please don't hesitate to get in touch if at all interested. So I'm going to be talking about the project I've been working on during my current research stay at the Caltech's infrared Processing and Analysis Center, where I've been working under the supervision of George Helou. Well, first I'd like to take a step back and provide some context on why we're doing this. We're essentially looking at moving objects. So in astronomical images, when not tracked, moving objects are moving very fast with respect to the background sky, which means that they will leave signature tracks of light in long exposure images. So these sort of objects can either be artificial, so satellites, space debris, or natural, so mainly comets and asteroids. So the very fast ones are the satellites and space debris. They're moving very, very fast, which means that for any long exposures, they will probably be crossing the whole field of view. We're not going to be focusing on them today. We're going to be focusing on asteroids and comets. So moving much, much slower. So from 0.1 to 1 arcsecond per second, which means that for typically a 30-second exposure, they will leave about 200 pixel trails. So why do we care about asteroids and comets? And here I'm going to be focusing more on asteroids, which have remained almost unchanged for the past 4.6 billion years. So since the assembly of the solar system. This means that by learning more about these objects, we can get very important insights into this assembly process. But not only we care about these objects because of scientific purposes, but also some of them are passing very close to the Earth's orbit, which means that they potentially they pose a threat of colliding with the Earth and causing local and global damage. So our current problem is that very big asteroids, such as the one that killed the dinosaurs, are very well understood and monitored. But we don't really know much about the small to medium-sized asteroids. And that is a problem because so an asteroid of only 10 meters across upon impact will release as much energy as a nuclear bomb. And since the energy release goes to the cube of the size, an asteroid of 100 meters across will release as much energy as 1,000 nuclear bombs. So this will only be in an area of a few square kilometers, which means that it's extremely unlikely that it's going to harm anyone because most of the Earth's surface is just covered with water. But it does happen sometimes. So 10 years ago in Russia, there was the Chelyabinsk event, which is a collision that harmed 1,500 people and caused $27 million worth of damage. So by characterizing the orbits of these objects, we can help mitigate or even prevent local global damage in our societies. And more specifically, finding an asteroid, even if we knew about it before, can help us improve our knowledge on its orbit. And the very nice thing about working with asteroid orbits is that they remain almost unchanged over time. They don't suffer any major perturbations, which means that looking at ancient data or archival data, even if it's a few years old, can help us learn where those asteroids are today. And this, all of this orbit information and asteroid information is actually sent to and managed by the Minor Planet Center, which is here at the CFA, and is the body that's overseeing all the data insights into asteroid orbits. So in this sense, our work has been focusing on the Strict Transients Facility, which is a telescope in the Palomar Mountains in California, and it has an extremely large field of view, 47 square degrees. And so it, for asteroid detection, it uses typically 30-second exposures and what are called difference images. So the idea of difference imaging is to take the direct science frame and then perform a subtraction with what's called a reference image, which is a very deep, very clean image with a very narrow PSF. And the result of that subtraction, as you can see, is that only any objects that are changing from one image to another will remain, basically transients. So that makes it so much easier to try to find any moving object or any transient in this type of images. So here in particular, you can see this I'm getting there. Is that wait, your question?
Yeah, I
sorry.
was wondering, what are the vast
Yes.
majority of things are not asteroids, so what they are?
And sorry, was that?
Yeah, I was just wondering when you say, detects whether it's a real streak or not, does that mean by any kind of object? The streak is made by any kind of object or?
Right, so the very first algorithm that just detects any streak-like features, so they can be, so sometimes they can be just the result of batch abstraction in the difference imaging. They can be cosmic rays, they can be some optical aberrations that they call here dementors and ghosts. They can be, so if you have a very bright star, there's normally going to be masked by the difference imaging process, but if it's very, very bright, it's going to have upcoming flares that are going to look like streaks. And then finally, we have these satellite trails that we've been talking about. They do, they're normally easy to tear apart because there's much longer, but sometimes, depending on the position of the satellite, they might get confused with just like a very fast asteroid. Anyway, but all these objects, the current pipeline picks them up and thinks that they are asteroids. And then there are two other steps, the machine learning classifier, and then people who have to look at these images and say, okay, they are asteroids or they're not. So the whole idea of this project was, can we make a pipeline that's able to recover as many asteroids as the current pipeline, while decreasing this massive rate of full detections? And even are we able to find some asteroids that are currently being missed out by the current pipeline? So those are the three questions that we're trying to answer here in this work. So for this, the main idea has been to use a convolutional neural network, and more specifically, a model called TOPO, which is an algorithm that was initially developed to try to find earthquake cracks in buildings. So any cracks in the facade, you will feed the algorithm just the image of a building, and it will tell you whether there were any cracks left by earthquakes on it. So it's being retrained by me to try to identify these moving objects, because and it's worked well, because at the end of the day, it's just trying to find some line-like features in optical images. So more specifically, you will feed it the original image, and it will output a probability heat map that's telling you how likely an object is to be an asteroid. Just for you to compare, that's the overlay detection to the original image. It's important to say that the algorithm outputs probabilities. This probability heat map, when the darker the object is, the more likely it is to be an asteroid. So there's a thresholding step that needs to be, there's a thresholding criterion that needs to be decided upon to consider whether these detections are or not asteroids. So we tried a wide range of threshold criteria. And so you can see here that the more aggressive the thresholding is, the more likely you are to leave out some objects that might potentially be asteroids, but also you get rid of some false positives, because if you have more linear thresholding, then you're likely to have to be picking up some objects that are not actually asteroids. So TOPO is a supervised learning algorithm, which means that we have to feed it with images of asteroids and tell it that they were actually asteroids. And more specifically, it was fed with three types of data sets. So the first one was comprised of real asteroids, then one with simulated asteroids, and then one that was mixed of both. So the real asteroid data set was comprised by 450 asteroids that had been detected by the pipeline currently in operation, so the current CTF pipeline, and they are confirmed asteroids by the CTF, so we know that they are actually real. The problem is that we're not looking to exactly reproduce the results of the current pipeline. We want to see whether we can find something else. So we only use the streaks that are detected by the current pipeline. We might be reproducing some current biases and skewing our results towards the specific type of asteroids that are currently being found. So to try to overcome this, we wonder, can we push the algorithm towards trying to find new objects? Sorry. So with this purpose, we injected 20,000 synthetic asteroids with a magnitude and track length distribution that will more or less follow that of the real objects. And we will inject the streaks in each frame by convolving it with the individual point spread function of each image to ensure that they will look as realistic as possible. So you can see here, this is the distribution of the real objects in terms of magnitude and length of track. And this is the distribution of the objects we created. So you can see that it's certainly trying to follow that of the real asteroids, but it's trying to fill in some of the gaps that are in the current detection to see whether there were some asteroids that were being messed up. You can see that we've ignored these points over here because they correspond to very bright asteroids that are normally very easy to find, so we're not too worried about them. Finally, we also injected some of these, so there were some of these streak-like features in our training set to teach the algorithm to not pick them up. So as we saw earlier, we had this ghost, we had this satellite trails, we had fast extraction, we had what's called the mentors, or very bright star, or finally cosmic rays. So to test the performance of our algorithms, so the one trained with real streaks, the one trained with synthetic streaks, and the one trained with a mix, we applied the 3 trained models to a set of 115 asteroids that were real, confirmed, and detected by the current pipeline, but that had not been involved at all in the training process. And just to as a reminder of this thresholding step, which can lead to more false positives, this is more linear, and less false positives, but less completeness, which is a way to talk about how many asteroids out of the asteroids that there are have been found. So the more aggressive thresholding will lead to less completeness, but also less false positives. So what we did was we compared the performance of these 3 models against the different thresholding criteria. So you can see here so obviously the path-fill algorithm will have 0 false positive rate and 1 incompleteness. And as you can see here in the curve, the more the higher it goes in terms of completeness, the more it shifts to the right, so the more false positives appear. In any case, so the perfect classifier will look like that, and it will have an area under the curve of 1. So anything coming close to it, the closer it is to the top left corner, the better the classifier is. So in this case, you can see the performance of the 3 models, the one trained with real, the one trained with synthetic, and the one trained with mixed, was all very good. So more specifically, if we take the best thresholding criterion for each curve according to this graph, then we will get a completeness of 98% for the one trained with real streaks and a precision of 90%, which means that out of every 100 detections, there are 90 that are real asteroids, there are 10 that are mistakenly taken as asteroids. It's 96, 92 for the one trained with synthetic, and 94, 95 for the one trained with the mix. So what we can infer from all of this is that actually the synthetic streaks were looking realistic, because the model trained with the synthetic streaks was able to perform as well as the one trained with the real streaks. And this is good news for us because it implies that we can enlarge the current training set, which is very small. There are only a few hundreds of real streaks that we can take and use for training. We can enlarge the training set by injecting synthetic streaks at no harm for the performance and the completeness of the algorithm. And this is positive because it means that we can potentially explore with this synthetic streaks that have turned out to be very realistic, whether we can see other types of clusters that haven't been found before. We also look at the endpoint determination, and so the beginning and endpoints of the track. And this information is very important because it's what's normally used for determining the orbit of the asteroids, and is what's sent to the minor planet center. So the error when finding the endpoints for the 3 models was about 12 pixels. So you can see the distributions are similar with some extra outliers in some of the models, but the distributions are very similar for the 3 models. The idea is not really to use the output of this fitting directly for orbit determination, because at the end of the day, 12 pixels for streaks that are 100 or 200 pixels long is a large error, is a large uncertainty, but rather to use these as reference values to narrow down the search for PSF fitting. So normally, to perform PSF fitting, if you had to do it on the original image, you'd be doing it on images of 3000 by 3000 pixels. By using the endpoint, so this like coarse endpoint information that we've retrieved from the model, we can be performing PSF fitting on very small cutouts, which will lead to when we use this coarse information and we did PSF fitting, this led to the exact endpoints that had already been reported to the archive. And finally, the last question that we wanted to answer was, are we able to find something new? The question is, the answer is we still need to look into it. So there were, with the model trained with the synthetic streaks and the model trained with a mix of synthetic and real streaks, there were some additional object candidates that were found. So we still need to do some further analysis on the PSF and other metrics to figure out whether they are real objects or not. But some of them seem promising, which means that we need to test it on a much larger test set instead of just 150 images. But we might be able to find some of the streaks that had been left out by the current CTF pipeline. So in terms of outlook and next steps, we can see that on the test set, the total algorithm was able to find at least as many objects as the current CTF pipeline, but with a much higher precision rate of at least 2 orders of magnitude larger, which means that Topo can potentially complement or even substitute this very first stage of the current pipeline that's picking up so many streak-like objects, but many of them are false positives. We need to, the next step after this is to apply Topo to live data and compare it to the 2 subsequent stages. So the stage where there's a machine learning classifier and the stage where there are human scanners. The reason why we haven't done this direct comparison before is because the statistics on their performance are only saved for a very short period of time. So we need to apply it to actual live data on the fly to check how it compares to their performances and see whether we can potentially use Topo again to complement or even substitute any of these 2 further stages, because ideally we want a pipeline that doesn't need human scanners looking at the images every night. Then we also need to look into, as I said, the metrics and the physical characteristics of these new candidates to find out their properties. And the idea is that these tools can be applied to not only CTF, but also other white field surveys. So they've already been applied successfully to screen images taken with the VOT survey telescope in Parnell, Chile. And they will now be applied to the Euclid images, which have very similar characteristics to those of BSD. Yeah, thank you very much.
Right, so we have questions for Belén. Yes, Joe.
You go back to that slide a couple back where you show those streaking. Yeah, is that the same images?
Yeah, that's the same image.
So you're saying that your uncertainty of the endpoint is 12 pixels. That seems fairly large compared to.
Right, so, but we're not using the endpoint positions to directly do orbit determination. We're just using the coarse endpoint positions to do PSF fitting. So actually with those 12 pixels uncertainty, we'll take a cutout of say 200 by 200 pixels, and then we would do PSF fitting, and then that will retrieve the exact endpoints that were reported to the archive. So 12 pixels is not is large if you were to use it for orbit determination, but not if you want to do PSF fitting afterwards.
One other quick question. Do you use any information from your catalog, for example? You know where all the point sources are. Do you automatically reject, things that are found right on top of a bright star or variable star positions? If you had an object that was variable, you know where that is, so you wouldn't.
So you get rid of the you need to get rid of objects like this?
Right.
Yeah, so it seems like we don't need it so far, because it seems like the machine learning algorithm has learned to not pick them up. If we had many false positives of objects like this, then we would use the catalog information.
We have an online question.
Oh, okay, let's go ahead with online and then Doc. Go ahead, first online.
Yes, thank you for this very interesting talk. So just to make it clear, because to me the most exciting part of this work is the synthetic population. So just to make this completely clear, are you effectively interpolating in asteroid parameter space, let's say, so that to make an educated guess for asteroid features that have not actually been observed? Is this what you're doing, and you're finding that this works?
Right, so we so far we haven't taken real asteroid physical parameters to simulate the synthetic asteroids. We've only done a more rough distribution, trying to follow a real distribution of magnitude across magnitude versus length of track. But the idea is, once we've proven, which we believe we have, once we've proven that these synthetic asteroids do in fact look realistic and can be safely used, the idea would be to try to create synthetic asteroids that look specifically like those asteroids that we think can be found but haven't been found yet. So to answer your question, yes, that's what we're planning to do. We haven't done that yet. We've done the step just before to check whether we were going to be able to do that or not.
Okay, great, thanks.
Thank you.
So related question, I guess. You had a plot with a bunch of green points, and it said green was found and red was not found, and there were no red points.
Oh, sorry. Yeah, that was a mistaken label.
Oh, okay. But I guess where I was going with that is your synthetic injected asteroids seem to be roughly the same part of the space in terms of length and brightness.
Mm-hmm.
And you can make them as faint as you want. So I was wondering why you didn't push them fainter until you can't detect them and kind of find where that.
Right. So we
that seemed like exactly what you were setting up for.
Yes. So right. So we did push this line harder. So we did see whether there were objects that we hadn't found there, and the answer so far was no, it didn't work as well when using this. So the problem is there is a reason. There is a reason why the real distribution looks like this, and it's because if you the longer the streak is, the light is distributed over more pixels, which means that the magnitude of each individual pixel actually goes down. So if you take, let's say, magnitude 19, then these streaks here are going to look more or less like magnitude 19. But if you go up to 160 pixels, then each pixel is not going to have magnitude 19. It's going to have a much higher magnitude. So there aren't actually that many asteroids in this space that can't be visible in terms of SNR.
Yeah, I guess I was just expected to see you push it until
A bit more?
until you fail.
Right, so we did push it more and it didn't work, so we went back to a more conservative
Okay.
approach.
And then I guess the other side of that is you can do that with real asteroids too. There
Yes.
are something like 500,000 rainbow asteroids in the Carolines, right there.
Well, there are
Probably this
about
one.
40,000 actually near Earth objects, so we know, well, actually, I have. Yes, yes.
But the point is your field of view is more than 1,000th of the sky, so you should have lots and lots and lots of them in every image, right?
No, so not that many actually, because it depends a lot on our relative position to this asteroid. And actually, we haven't looked, so I know the key point of the project, we're not really looking at absolute completeness, right? We're not looking at how many asteroids are the real asteroids that there exist have we found. It's more a local completeness, as in how does it compare to this current algorithm. But in terms of the, so we expect to maybe find some asteroids that have been left out, but not that many, because actually, even if we take the steps towards what you're saying would be to take a known asteroid, take their orbit, its orbit from the catalog, and propagate it backwards and see where it would be in the archive and how would it look. And the problem with this is that often when we see an asteroid and we find it and we detect it, that asteroid then goes away relative to us. So it's no longer visible. So we will have to take all these known asteroids, propagate the orbit backwards and see whether they're visible or not in these images. But the answer to that is not as many as one would think. So we expect to maybe find some new ones that have been left out, not that many.
Okay.
Thank you. Well, it's 1 p.m. actually, so you are all welcome to grab a sandwich outside and continue asking questions about Festa and Belén. Other than that, thank you very much for joining us.